Hi doctor, hi everyone. We are first year biomedical engineering students from Faculty of Engineering. Today we would like to explain about our group assignment about below knee prosthetics. I'm Kavita Shri Anaparupan K. Tanabalan together with Arini Vijay Kumar, Yashwini Raghavendra Tayalan and Arya Yamna would like to explain about this below knee prosthetics.
Hello, Doctor. I'm Arlena, and our presentation is about below-knee prosthesis. So this report examines the mechanical aspect of below-knee prosthesis, focusing on statics, mechanics, and stress analysis to ensure durability and comfort. Key elements, like free body diagram, axial load, bending, torsion, and stress, are analyzed to confirm the prosthesis can withstand daily activities without deformation. Using measurements from the University Malaya Center of Prosthetic, this study highlights areas for improvement, emphasizing advanced material and better load distribution to enhance functionality, comfort, and lifespan, ultimately improving users' quality of life. Our objectives are number one, to perform equilibrium-based analysis using free-body diagrams. Number two, to analyze axial, bending, and torsional loads on the prosthetic. Number three, to calculate moments of interior for critical components. Number four, to evaluate stress and deformation under typically used conditions. And lastly, number five, to propose improvements based on the analysis. Now let's move to talk about the structure of prosthetic below knee. First we have the socket, the part that fits over the residual limb, made of either thermoplastic, fiberglass, or silicone. Next we have the pylon, acts as the structural support connecting the socket to the foot. The materials are made of with either aluminum, steel, titanium, or carbon fiber composite. And lastly we have the foot, mimics the function of a natural foot, made of either carbon fiber, polyurethane, or plastic and composite. Each part is tailored to the user's needs, with consideration for weight, activity level, and cost.
So I would like to explain about methodology. First, we went to the Center of Prosthetic and Orthotic Engineering to ask permission and arrange the schedule to take a picture of below knee prosthetic. Then, a briefing and explanation about below knee prosthetic were given by staff, followed by we identified various types in below knee prosthetic and took a picture of them. You guys can see in the slide. Then, all the structure in below knee prosthetic was measured using measuring tape, followed by all the data that had been collected was jotted down. The staff also lent us a manual book of prosthetic to look at the below knee prosthetic measurements. Finally, a report was written based on the observation, calculation, and the result that were gained. So now I would like to explain about calculation and results. We have a three aspects. First is free body diagram and orthographic projection. Second is axial bending, torsional load and movement of inertia. Third is stress and deformation. Now we will look at the free body diagram and orthographic projection. So first we will look at the free body diagram. Basically three forces acting on this below knee prosthetic. First is normal force acting upwards. We represent as a N and also known as a F reaction. The second force is F prosthetic, also known as a weight, which is acting downwards. We represent as a letter W. The third force is force applied at prosthetic foot, which is acting upwards, and we represent as a letter P. When a below knee prosthetic is in equilibrium, the total force and total movement is equal to 0. As you guys can see in the free body diagram, all the force is acting on y-axis. So total force on y-axis is equivalent to 0. We also can write negative F prosthetic plus F reaction plus FB is equivalent to 0. We also assume movement at the prosthetic foot is equivalent to 0. Where we also can write negative 0.1 times F reaction plus 0.1 F prosthetic is equivalent to 0. We use 0.1 because this is the measurement that we got from the calculation. This is the distance between weight normal force to the force applied at prosthetic foot. Now we draw free body diagram for the overall below knee prosthetic. as you guys can see in the slides. We also draw free body diagram for each component of the below knee prosthetic. First is the socket, only had the 2 force, normal force and weight. Pylon got extra 1 force, which is called as a force applied at the prosthetic foot. We represent as a letter P. And the last one is at foot, also got 2 force, normal force and weight. This is the orthographic projection: front view, side view, top view and bottom view, as you guys can see in the slides. Axial, bending, torsional load and moment of inertia. First we will look at the axial load. So for the calculation, we use assumed value that we got from the observation. For the axial load, we find the axial stress, which is axial stress equivalent to F over A. So for the A is represented as the area. For the A, we use the diameter that we got from the observation, which is 0.04 meter. So for the area, we use D for a power of 4 over 4 as a formula, and we got 5.062 times 10 power of negative 4 as our area. We substitute in the axial stress formula. For the F, we assume the body weight through prosthesis is 700 Newton. So we got 1.39 times 10 power of 6 Pascal. So we represent 10 power of 6 as a mega. So we got 1.39 megapascal. Next, we calculate the moment of inertia. Moment of inertia is equivalent to 1 over 12 B times h power of 3. Also equivalent to pi over 64 times d power of 4. For the d value, we use the value from the observation. So I equivalent to pi over 64 times 0.04 power of 4. So we got 1.2566 times 10 power of negative 7 as our moment of inertia. Then we calculate the bending load. Bending load is equivalent to negative my over I. M is bending moment. So bending moment we assume as a 50, and y is the radius of pylon. So as we calculate from the measurement, we got 0.04 as our diameter. So the radius is 0.02 and 50 is the assumed value over I. As we calculate from just now, we got the value negative 7.96 times 10 power of 6 Pascal. So 10 power of 6 we replace as a mega. So we got bending load is equivalent to negative 7.96 megapascal. Then we go for the torsional load. So torsional load equivalents to tor times radius over j, or also known as a moment of inertia. So for the tor, we assume the value is 30. So the torsional load equals to 30 times 0.02, as our diameter is 0.04 over moment of inertia as we calculated before. So we got 477.5 times 10 power of 6 Pascal. So 10 power of 6 we convert into mega. So torsional load we got 477.5 megapascal. Now we will look at the stress and deformation. First we calculate deformation due to axial stress. So for the deformation due to axial stress, we will calculate the change in length. So change in length is equivalent to F times L over AE. So F is the force, as we assumed just now, it is a 700 Newton. L is length of the pylon. Just now we used diameter of pylon. Now for this formula we use the length of pylon, which is we got from the observation, over area we already calculated just now, times E. E is the Young modulus of material. So we choose titanium. Later we will discuss why we choose titanium. So the Young modulus of titanium is 110 times 10 power of 9. So the change in length we got is 6.28 times 10 power of negative 6. We converted 10 power of negative 6 to micro. So the change in length we got is 6.28 micrometer. Next, we move to the bending stress and deformation. For bending stress and deformation, we will calculate the bending deflection. So, bending deflection is equivalent to m times L square over 8EI. So, m is a bending moment, as we assumed just now, is 50 times with 0.5 square. 0.5 is the length of pylon, which is got from the observation, over 8 times E is the Young modulus, as I mentioned just now. For titanium is 110 times 10 power of 9, and I is the moment of inertia, which is got from the previous calculation. So the bending deflection is 1.13 times 10 power of negative 4 meter. Lastly, we calculate the torsional stress and deformation, which is unchanged. For torsional stress and deformation, we calculate the angle of twist. So the angle of twist is equivalent to T times L over JG. So T is the torque, as we assumed just now, is 30, and L is the length of pylon from the observation. J, moment of inertia, as we calculated in the previous calculation. G is the shear modulus for material. For titanium is 44 times 10 power of 9. So angle of twist that we got is 2.71 times 10 power of negative 4 in radian. If we converted to degree, we got 0.0275 as our angle of twist.
Hi, I'm Harini. Let's begin the discussion about the fundamental forces acting on the prosthetic. First is free body diagram. The free body diagram illustrates all forces including body weight, ground reactions, and external loads. It ensures prosthetic stability by accounting for forces acting on the socket, pylon, and foot. Using the static equilibrium principles, we ensure that forces and moments balance to maintain stability. Second is axial load analysis. Axial forces are distributed evenly along the prosthetic structure. The calculated axial stress is 1.39 megapascal, which is relatively low, ensuring that the design can withstand weight without material failure. Third is bending load and stress. Bending loads are crucial, especially during the dynamic activities like walking and running. The highest bending stress occurs at the knee joint, recorded at negative 7.96 megapascal. This requires the material to possess high bending resistance to prevent deformation or failure. Fourth is torsional load and stress. Twisting and turning movements generate torsional stress in the prosthetic. The calculated torsional stress is 477.5 megapascal, which is quite high, meaning the design must resist torsion to avoid failure. Fifth is moment of inertia. Moment of inertia is a key factor in measuring resistance to deformation. A higher moment of inertia ensures structural integrity under load and minimizes deformation, enhancing user comfort. Sixth is material, which is titanium. Titanium was chosen due to its excellent strength to weight ratio and corrosion resistance. It effectively resists bending and torsional stress while providing durability and comfort for the users. Finally, let's discuss stress and deformation behavior in the prosthetic. Hooke's law and material behavior. According to Hooke's law, stress and strain are proportional up to the elastic limit, ensuring the material returns to its original shape after load removal. The stress and strain graph shows different zones, which is elastic zone, plastic zone, strain hardening zone, and failure zone. Understanding this behavior helps optimize the prosthetic design to balance strength and the flexibility.
Limitations. First, fit and comfort related issues. The challenge is achieving optimal fit and comfort. Socket fit must match user's anatomy to avoid discomfort and pressure sores. Limb volume changes. It varies due to age, obesity, or muscular atrophy. Customization difficult and time consuming to modify sockets for each user. It results in chronic issues with ideal fit, reducing prosthetic effectiveness. Second, Limited range of motion. The issue is limited motion in some prosthetic designs. Second, trade off. Stability and load bearing often reduce mobility. Third, natural motion. It is difficult to replicate intricate limb movements. Fourth, impact. It inhibits freedom of movement and quality of life. Finally, the solution. It requires innovative designs and materials to enhance motion without losing stability. Improvement. First, improve socket design. The solution is to use 3D scanning and printing for better personalization. Benefits: it enhances accuracy and reduces discomfort and fewer pressure sores. Third, adaptive materials. It adjusts to limb dimension changes, improving its fit. Finally, the outcome: better use experience and longer device lifespan. Second, limited range of motion. The solution is flexible adaptive joint mechanisms for natural movement. The materials: lightweight fiber reinforced polymers and composites. Third, the benefits: increased flexibility, maintained strength and durability. And the outcome: greater freedom of movement and improved quality of life.
Conclusion: the below knee prosthesis demonstrates durability and strength under various mechanical stresses thanks to the use of titanium. However, challenges remain with fit, comfort, and limited joint mobility. Advances in socket design, flexible joint mechanisms, and adaptive materials can address these issues, enhancing user comfort, fit, and mobility. Modern technologies and biomechanical innovations are driving improvements in prosthetic design, aiming to restore mobility and independence, ultimately improving the quality of life for users.
This is our reference. We mostly took from internet website such as Physiopedia, Scholar Hub, and we also refer to some manual books. That's all from us. Thank you so much.